Hello there, and welcome to The Weary Researcher, where we explore the universe's biggest mysteries at a pace that won't keep you tossing and turning all night. Tonight, we're embarking on a gentle journey through one of the most profound questions humanity has ever asked. If the cosmos is so vast and filled with countless worlds, where is everybody? Before we drift into the cosmic silence together, I'd love to know where in the world you're listening from tonight. I've heard from Nakuru City in Kenya, all the way to Brisbane, Australia, from San Salvador, El Salvador, to Paris, France, and many listeners from North America. I appreciate all of your support, so please drop a comment and let me know your corner of the world and what time it is there. It's always fascinating to see just how far these stories travel. And if you find these gentle explorations through space and science helpful for winding down, I'd be extremely grateful if you gave this video a like and perhaps subscribed for more cosmic inquiries. It helps other curious souls find their way to this peaceful corner of the internet, where big questions meet bedtime contemplation. Now, I do hope this video strikes just the right balance, fascinating enough to engage your mind, but soothing enough to let you drift off peacefully. Though if it does happen to keep you awake with wonder, well, at least you'll fall asleep a little wiser about our place in the universe. So settle in, get comfortable, and let's explore together why the night sky might be far more silent than we ever expected. Picture this. You're lying on a blanket in a field far from city lights, gazing up at the Milky Way stretched across the darkness like spilled cream. Above you, hundreds of billions of stars twinkle in the cosmic breeze, each one potentially warming worlds of its own. The scale is breathtaking, almost incomprehensible. Our galaxy alone contains more stars than there are grains of sand on every beach on Earth. And beyond our galaxy, hundreds of billions more galaxies, each with their own stellar cities, stretching away into infinity. With such an abundance of cosmic real estate, with so many potential homes for life, you might expect the universe to be buzzing with activity. Radio signals crossing interstellar space, evidence of vast engineering projects, perhaps even visitors dropping by to say hello. The mathematics of probability seems to whisper that we should not be alone. And yet, as you lie there under that star-drunk sky, the silence is profound. No alien broadcasts interrupt your peaceful contemplation. No mysterious lights dart between the constellations. Just you, the stars, and an almost overwhelming quiet. This is the heart of what scientists call the Fermi Paradox, named after the brilliant physicist Enrico Fermi. It's not really a paradox in the strict mathematical sense, but rather a profound puzzle that has been keeping scientists, philosophers, and curious minds awake at night for decades. The contradiction is beautifully simple, yet deeply unsettling. The universe appears perfectly suited to harbour countless civilizations, yet we've found no convincing evidence that any exist beyond our small blue world. The story begins on a summer day in 1950 at Los Alamos National Laboratory in New Mexico. Enrico Fermi, the man who helped usher in the atomic age, was walking to lunch with three colleagues: Emil Konopinski, Edward Teller, and Herbert York. The conversation had drifted, as conversations often do among physicists, from the mundane to the cosmic. They'd been discussing recent UFO sightings in the news, perhaps with the gentle skepticism that scientists bring to extraordinary claims. But then, in the middle of their meal, Fermi suddenly looked up from his food and asked a question that would echo through the decades. Where is everybody? His colleagues understood immediately. If the galaxy were teeming with advanced civilizations, as the statistics seem to suggest it should be, then where were the signs of their existence? Where were their signals, their spacecraft, their great works of engineering that should be visible across interstellar distances? Fermi's question wasn't born from a moment of whimsy. He was one of the most rigorous thinkers of his generation, a man who could perform complex calculations in his head and had an almost supernatural intuition for the underlying patterns of nature. When Fermi wondered about something, other scientists paid attention. His casual lunchtime query would eventually blossom into one of the most important questions in astrobiology, cosmology, and the search for extraterrestrial intelligence. The paradox has only grown more acute in the decades since that lunch conversation. In Fermi's time, we knew of no planets beyond our solar system. The existence of other worlds was pure speculation, the stuff of science fiction rather than scientific fact. Today we've discovered thousands of exoplanets, with new ones being catalogued almost daily. We've found worlds orbiting in the habitable zones of their stars, where temperatures might allow liquid water to exist on their surfaces. We've identified super-Earths and mini-Neptunes, hot Jupiters and frozen wastelands, painting a picture of a universe rich with planetary diversity. Every new discovery seems to make the emergence of life elsewhere more probable, not less. Yet the cosmic silence persists. The radio telescopes that scan the heavens detect pulsars and quasars, the birth cries of stars, and the death screams of black holes, but no clearly artificial signals from distant civilizations. The space telescopes that peer into the depths of the universe see galaxies forming and colliding, supernovas painting the darkness with heavy elements, but no signs of vast engineering projects or stellar-scale construction. This absence is what makes the Fermi Paradox so compelling and so troubling. It's not simply that we haven't found aliens yet, it's that we haven't found any trace of them at all, despite the fact that our improving technology should make such traces easier to detect. We're not just looking for little green beings in flying saucers, we're looking for any sign that intelligence has emerged somewhere else in the cosmos and left its mark on the universe. Consider the timeline. Our galaxy, the Milky Way, is approximately 13 billion years old. Earth formed about 4.5 billion years ago, and life appeared relatively quickly in cosmic terms, perhaps within the first billion years. But for most of Earth's history, life remained stubbornly simple, single-celled organisms content to float in ancient seas. Complex, multicellular life didn't really take off until about 600 million years ago, and human civilization is a mere blink of an eye, emerging only in the last few thousand years. But here's the thing. If life had emerged on a world just a few million years earlier than it did on Earth, that civilization would have had an enormous head start. 1 million years might sound like a long time to us, but in cosmic terms, it's negligible, barely a moment. Yet in that brief span, a technological civilization could potentially colonize an entire galaxy. They would have had time to spread from star to star, to build structures visible from interstellar distances, to fill the radio spectrum with their communications. The math is sobering. Even with relatively modest technology, travelling at perhaps 1% of the speed of light, a civilization could reach every star in the galaxy within about 10 million years. That sounds like an eternity to us, but remember, our galaxy has been capable of supporting life for billions of years. There has been ample time for multiple waves of expansion, for countless civilizations to rise and spread across the stars. And yet, when we look up at the night sky, we see no evidence of this grand colonization. No artificial structures orbiting distant stars. No clearly technological radio signals. No signs that anyone has been rearranging solar systems to suit their needs. The universe appears, from our perspective, to be entirely natural, entirely devoid of the fingerprints of intelligence. This is where the Fermi Paradox begins to feel less like an academic puzzle and more like a mystery with profound implications for our own future. If advanced civilizations should be common, but we see no evidence of them, then something is filtering them out. Something is preventing life from reaching the level of technological sophistication needed to become visible on cosmic scales. The possibilities are not all comforting. Perhaps life itself is far rarer than we imagine, requiring such an unlikely confluence of conditions that Earth represents a virtually unique occurrence in our cosmic neighbourhood. Perhaps intelligence is a fluke, an evolutionary accident so improbable that it almost never happens twice. Perhaps civilizations tend to destroy themselves before they can spread to the stars, victims of their own technological power or their inability to solve the challenges that come with advanced capabilities. Or perhaps they're out there, but they're hiding. Maybe the galaxy is full of civilizations that have learned to keep quiet, to avoid drawing attention to themselves. Maybe there's something in the dark between the stars that makes silence a survival strategy. Maybe the universe is not the welcoming place we imagine it to be, but rather a dangerous neighborhood where it's best to keep the lights off and the doors locked. These possibilities form the backbone of what scientists call solutions to the Fermi Paradox, though solutions might be too optimistic a word. They're more like possible explanations, each with its own implications for humanity's place in the cosmos and our prospects for the future. Some suggest we are alone, or nearly so. Others suggest we are being watched, studied, perhaps protected. Still others suggest we are living in a universe far more dangerous than we dare to imagine. But before we explore these darker possibilities, let's take a step back and consider the question more systematically. To understand why the absence of detectable alien civilizations is so puzzling, we need to understand just how many opportunities for life the universe appears to provide. We need to look at the numbers to see why statisticians and scientists expected to find evidence of extraterrestrial intelligence by now. The framework for thinking about this question was provided by astronomer Frank Drake in 1961. Drake wasn't trying to calculate the exact number of alien civilizations, a task that would have been impossibly speculative. Instead, he was trying to organize the problem, to break down the grand question of how many detectable civilizations are out there into a series of smaller, more manageable questions. The result was what we now call the Drake equation, a formula that has become one of the most famous equations in science, despite the fact that most of its terms remain almost completely unknown. The equation doesn't give us answers so much as it gives us a map of our ignorance, highlighting the specific questions we need to answer to understand our place in the cosmic community. The Drake equation considers several factors: the rate at which stars form in our galaxy, the fraction of those stars that have planets, the number of planets per star that could potentially support life, the fraction of those planets where life actually emerges, the fraction where intelligent life evolves, the fraction where that intelligence develops technology capable of communicating across interstellar distances, and finally, the length of time such civilizations survive and remain detectable. When Drake first wrote down his equation, most of these terms were pure guesswork. We didn't know if other stars had planets at all, let alone how common they were. We had only one example of life in the universe, our own, making it impossible to estimate how likely life was to emerge elsewhere. We had only one example of intelligence, again our own, making it equally difficult to guess how often intelligence might evolve. But in the decades since Drake first posed his question, we've made remarkable progress on several of these terms. The discovery of exoplanets has been perhaps the most revolutionary development, completely transforming our understanding of planetary systems and their potential for harbouring life. The journey began slowly, with indirect detections and controversial claims. But in the 1990s, the first confirmed planets around sun-like stars were discovered, strange worlds that challenged our assumptions about how planetary systems form and evolve. These early discoveries revealed hot Jupiters, massive planets orbiting incredibly close to their stars, completing their years in a matter of days. As detection techniques improved, smaller and more distant planets began to turn up. NASA's Kepler Space Telescope, launched in 2009, revolutionized the field by staring at a single patch of sky for years, watching for the tiny dimming that occurs when a planet crosses in front of its star. The results were staggering. Kepler discovered thousands of planets, revealing that planetary systems are not rare curiosities, but rather the norm. Most stars, it turns out, have planets. More importantly, for the question of life, many of these planets orbit in what astronomers call the habitable zone, sometimes nicknamed the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot and not too cold, but just right for the chemistry of life as we know it. The statistics are remarkable. Current estimates suggest that roughly 1 in 5 Sun-like stars has an Earth-sized planet orbiting in its habitable zone. Given that there are perhaps 50 billion Sun-like stars in our galaxy alone, this suggests the existence of billions of potentially habitable worlds in the Milky Way. Billions of places where the conditions might be right for oceans to form, for organic chemistry to flourish, for life to take its first tentative steps. This is where the Fermi Paradox becomes most acute. The universe appears to be not just capable of supporting life, but practically designed for it. Planets are common, habitable zones are common, the chemical elements necessary for life are abundant throughout the cosmos. Time has been plentiful, with billions of years available for life to emerge and evolve on countless worlds. And yet, despite all of these favourable conditions, despite the vast numbers of potential homes for life, we remain apparently alone. The radio telescopes that scan the heavens detect only natural phenomena. The optical telescopes that peer into the depths of space see only stars and galaxies following the laws of physics. There are no signs of intelligence, no evidence of technology, no indication that any other species has ever asked the same questions we're asking tonight. This silence is what makes the Fermi Paradox so profound and so unsettling. It suggests that somewhere in the chain from planets to intelligence to detectable civilizations, there's a bottleneck, a filter that prevents most worlds from producing the kind of technological species that could signal its presence across interstellar distances. The question then becomes, where is this filter? What is preventing the universe from being filled with the chatter of countless civilizations? The possibilities are both fascinating and sobering, each one casting a different light on our own existence and our prospects for the future. Perhaps the filter lies very early in the process, in the emergence of life itself. While we know that the building blocks of organic chemistry are common throughout the universe, the actual spark that transforms non-living matter into living organisms remains one of science's greatest mysteries. We call this process abiogenesis, and despite decades of research, we still don't fully understand how it happens. On Earth, life appears to have emerged relatively quickly after our planet cooled enough to support liquid water. This might suggest that the transition from chemistry to biology is relatively straightforward, given the right conditions. But it's also possible that we're looking at this backwards. Perhaps life emerged quickly on Earth not because it's easy, but because Earth is special in ways we don't yet recognize. Maybe the conditions that allow non-living matter to organize itself into self-replicating systems are far more restrictive than we imagine. Consider what has to happen for life to begin. You need the right chemical ingredients, certainly, but you also need them in the right concentrations, at the right temperatures, with the right energy sources to drive the reactions that build complex molecules. You need protection from radiation that would break apart delicate organic compounds, but not so much protection that you lack the energy needed for chemistry to occur. You need stability over long periods, but also enough change to drive evolution and complexity. When you start adding up all these requirements, Earth begins to look less like a typical planet and more like a remarkable exception. Our world sits at just the right distance from a star of just the right type. We have a large moon that stabilizes our axial tilt and creates tides that may have been crucial for early life. We have plate tectonics that recycle our atmosphere and regulate our climate over geological time. We have a magnetic field that protects us from harmful solar radiation. We orbit in a galaxy that's neither too active nor too quiet, in a region where heavy elements are abundant, but stellar explosions are rare. This line of thinking leads to what's called the rare Earth hypothesis, the idea that while simple life might be common throughout the universe, the specific conditions needed for complex life are extraordinarily rare. Under this view, we might expect to find microbes on many worlds, but complex multicellular organisms would be vanishingly uncommon. But even if we accept that complex life is rare, we still face another mystery: the nature of intelligence itself. On Earth, life existed for billions of years before anything resembling intelligence emerged. For most of our planet's history, the most sophisticated organisms were single-celled bacteria floating in ancient seas. Complex cells didn't appear until perhaps 2 billion years ago. Multicellular life is only about 1 billion years old. And what we might recognize as intelligence, the kind of problem-solving, tool-using, language-speaking intelligence that characterizes humans and a few other species, has existed for mere moments in geological time. This raises profound questions about the nature of intelligence and its role in evolution. Is intelligence inevitable, given enough time and the right conditions? Or is it an unlikely accident, a quirk of evolution that happened to occur on Earth but might never arise elsewhere? The answer has enormous implications for the Fermi Paradox. If intelligence is inevitable, then we should expect it to emerge on many worlds, given the billions of years available and the countless opportunities for evolution to experiment. But if intelligence is accidental, a random mutation that happened to prove useful in one particular environment, then it might be extraordinarily rare throughout the universe. Looking at Earth's evolutionary history doesn't provide much comfort for those hoping intelligence is common. Intelligence, as we understand it, has evolved independently very few times on our planet. Most successful species get by perfectly well without it. Bacteria have dominated Earth for billions of years without ever developing anything resembling human-like cognition. Many complex animals navigate their environments, find food, avoid predators, and reproduce successfully using instinct and simple learning rather than abstract reasoning. Even among the species we consider intelligent, the kind of technological intelligence that could build radio telescopes and spacecraft is rarer still. Dolphins are undoubtedly intelligent, but they're unlikely to develop space travel. Octopuses are remarkably clever problem solvers, but their short lifespans and solitary nature make it difficult for them to accumulate knowledge across generations. Even among our closest relatives, the great apes, only humans have developed the specific combination of traits that led to technological civilization. This suggests that even if life is common, and even if complex life occasionally emerges, the specific type of intelligence needed to build detectable civilizations might be extraordinarily rare. We might live in a universe teeming with life, filled with worlds where evolution has produced countless fascinating creatures, but where technological intelligence remains a cosmic rarity. But let's assume, for the sake of argument, that intelligence does emerge elsewhere in the universe. Let's imagine that on some distant world, evolution has produced creatures capable of abstract thought, tool use, and cumulative learning. Does this necessarily lead to the kind of technological civilization that we could detect from Earth? Here we encounter what might be called the civilization filter. Even if intelligence emerges, there's no guarantee that it will develop technology, and even less guarantee that technological civilizations will survive long enough to become detectable across interstellar distances. Consider our own history. Humans have existed as a species for perhaps 300,000 years, but we've only had technological civilization for a few thousand years at most. Radio technology, which forms the basis of most searches for extraterrestrial intelligence, has existed for barely more than a century. Spaceflight is less than 70 years old. From a cosmic perspective, our technological phase has lasted for essentially no time at all. This brevity raises uncomfortable questions about the longevity of technological civilizations. Perhaps the reason we don't detect alien signals is not that intelligence is rare, but that technological civilizations tend to be short-lived. Maybe there's something inherent in the development of advanced technology that leads to self-destruction. The possibilities are sobering. Nuclear weapons give civilizations the power to destroy themselves within decades of discovering atomic energy. Climate change might be an inevitable consequence of industrial development, leading to environmental collapse before spacefaring technology can be developed. Artificial intelligence might pose existential risks that few civilizations successfully navigate. Biological or chemical weapons might prove too tempting for warring factions to resist using, or perhaps the threat is more subtle. Maybe advanced civilizations tend to become so focused on virtual realities and artificial pleasures that they lose interest in exploring the physical universe. Maybe they become so risk-averse that they never venture beyond their home worlds. Maybe they develop technologies that make them undetectable to primitive civilizations like ourselves. This possibility leads to what's sometimes called the Great Filter, a hypothetical evolutionary bottleneck that prevents most life from reaching the level of technological sophistication needed to become detectable across interstellar distances. The Great Filter could be early in the evolutionary process, in which case we're remarkably lucky to have made it this far. Or it could lie ahead of us, in which case our own future might be more precarious than we'd like to believe. The concept of the Great Filter was popularized by economist Robin Hanson, who pointed out that the development of life from its earliest stages to spacefaring civilization requires passing through many evolutionary steps, each of which might be highly improbable. These steps might include the emergence of life itself, the development of complex cells, the evolution of multicellular organisms, the emergence of intelligence, the development of technology, and the ability to avoid self-destruction long enough to spread beyond a single world. If even one of these steps is extremely unlikely, it could explain why we don't see evidence of alien civilizations. The filter acts like a cosmic bottleneck, allowing only a tiny fraction of potential life to pass through to the next stage of development. From our perspective, the location of the Great Filter is crucial. If it lies behind us, in our evolutionary past, then we might be among the few species lucky enough to have made it through. In that case, the universe might be ours for the taking, with few competitors for the vast resources of space. But if the Great Filter lies ahead of us, then our situation is far more precarious. We might be approaching the same bottleneck that has claimed countless other promising civilizations. Our rapid technological development, rather than being a sign of our success, might be leading us toward the same fate that has befallen every other intelligent species in our galaxy. Recent developments in artificial intelligence have given new urgency to these concerns. Some researchers worry that the creation of superintelligent machines might represent a future Great Filter, a technological development that few civilizations survive. The reasoning is grimly logical. Any civilization that develops artificial intelligence will likely do so during a period of competition and conflict, when different groups are racing to gain advantages over their rivals. In such an environment, AI systems might be weaponized before their full implications are understood, leading to catastrophic consequences. But the Great Filter, while compelling, is not the only possible explanation for the cosmic silence. Perhaps civilizations do survive and thrive, but they've learned to keep quiet. Maybe the universe is not the empty wilderness it appears to be, but rather a dangerous neighborhood where it pays to avoid attracting attention. This possibility leads us into darker territory, to explanations for the Fermi Paradox that cast the cosmos not as a welcoming place waiting to be explored, but as a hostile environment where survival depends on stealth and secrecy. These theories suggest that advanced civilizations exist throughout the galaxy, but they remain hidden from view, either by choice or necessity. The most chilling of these explanations is known as the dark forest hypothesis, popularized by Chinese science fiction writer Liu Cixin in his acclaimed novel of the same name. According to this theory, the universe is like a dark forest, filled with armed hunters moving silently through the trees. Each civilization is like one of these hunters, aware that revealing their position might attract the attention of others, but never knowing whether those others come in peace or war. In the dark forest, the safest strategy is to remain hidden and to eliminate any other civilizations you discover before they can eliminate you. The logic is brutal but compelling, since you can never know the true intentions of an alien civilization, and since the stakes of being wrong are total annihilation, the rational response to discovering another intelligence is to destroy it immediately. Under this scenario, the galaxy might be teeming with civilizations, but they all maintain strict radio silence to avoid attracting unwanted attention. Any civilization foolish enough to broadcast its presence to the cosmos would quickly find itself the target of a preemptive strike from more cautious neighbours. The dark forest hypothesis explains the cosmic silence perfectly, but it paints a terrifying picture of our universe and our own future. If the theory is correct, then our own radio emissions over the past century have been like signal fires in a dark forest, announcing our presence to any hunters who might be listening. Our fate under this scenario might already be sealed. Most scientists find the dark forest hypothesis implausible, arguing that it requires universal hostility among all civilizations and doesn't account for the benefits of cooperation and communication that typically emerge between intelligent species. But the theory serves as a sobering reminder that the silence we observe might not indicate absence, but rather the presence of intelligences far more sophisticated and cautious than ourselves. A more benevolent version of the hidden civilization hypothesis is known as the zoo hypothesis. Under this scenario, advanced alien civilizations do exist and are aware of us, but they've chosen to observe us from a distance without making contact. Like visitors to a wildlife preserve, they watch us with interest, but refrain from interfering with our natural development. The zoo hypothesis suggests that there might be something like a galactic ethics code that prevents advanced civilizations from contacting younger species before they reach a certain level of maturity. Perhaps there are protocols in place, agreements among the galactic community about when and how to make contact with emerging civilizations. Under this view, we might be living in a kind of cosmic nature preserve, protected and observed, but not yet ready for full membership in the galactic community. Our radio telescopes might be scanning empty skies not because there's no one out there, but because they've chosen to remain undetectable until we're ready for the conversation. The zoo hypothesis has an appealing quality to it, suggesting that we're not alone, but simply not yet mature enough for contact. It implies a benevolent universe populated by wise and patient civilizations who will welcome us when we're ready. But like the dark forest hypothesis, it requires a level of coordination among alien civilizations that might be difficult to maintain. It would only take one rogue civilization breaking the quarantine to reveal the truth. As we drift deeper into these possibilities, it's worth considering what might be the most unsettling explanation of all: that we're simply looking in the wrong places, or perhaps more accurately, at the wrong time. The universe, after all, operates on scales that dwarf human experience. What we perceive as cosmic silence might simply be the quiet between conversations that span millennia. Think about it this way. If you were an alien astronomer studying Earth during the Cretaceous period, you would see a world teeming with life, but no signs of intelligence or technology. You might conclude that, while biology had emerged on this distant world, it had never developed the capacity for abstract thought or tool use. You would be wrong, but you would have no way of knowing it. Intelligence, when it finally emerged, would arrive in what would seem like an instant from your cosmic perspective. Perhaps this is our situation now. We might be like observers who have tuned into a vast conversation just moments before the speakers have paused for thought. The civilizations we seek might be in contemplative phases, having long ago moved beyond the noisy radio broadcasts and obvious megastructures that we're searching for. They might communicate through channels we haven't discovered yet, or they might have transcended the need for communication altogether. This temporal mismatch could work in the other direction as well. Maybe the galaxy was once alive with chatter, filled with the radio emissions of countless young civilizations discovering electromagnetic radiation for the first time. But perhaps that phase passes quickly in the lifetime of a species, the period when a civilization broadcasts unintentionally into space might last only a few centuries, before they develop more efficient, directed communication methods. If this is the case, then we might be living through our own brief noisy phase, the cosmic equivalent of a teenager learning to whisper in a library. The older, wiser civilizations around us might have long ago learned to communicate without spilling their signals across the galaxy for every primitive species to detect. Recent developments in our search for extraterrestrial intelligence have begun to grapple with these possibilities. The modern SETI programs, like Breakthrough Listen, represent a dramatic expansion in both scope and sophistication compared to earlier efforts. These projects scan billions of frequency channels across thousands of hours of observation time, analysing data with artificial intelligence systems that can detect patterns no human observer could recognise. The scale is breathtaking. Breakthrough. Listen generates more data in a single day than previous SETI projects produced in an entire year. It examines radio signals across a much broader spectrum, looks deeper into space, and processes information hundreds of times faster than earlier searches. If there are civilizations out there broadcasting in ways we can detect, these new efforts should find them. But perhaps the most intriguing development in SETI has been the expansion beyond radio astronomy. Modern searches now include optical surveys, looking for laser signals, analyses of stellar light curves that might reveal artificial megastructures, and even atmospheric studies of exoplanets searching for biosignatures or technosignatures that might indicate the presence of industrial civilizations. The James Webb Space Telescope, with its unprecedented ability to analyze the atmospheres of distant worlds, has opened entirely new possibilities for detecting life. It can identify water vapor, oxygen, methane, and other gases that might indicate biological processes. More intriguingly, it might eventually detect artificial compounds in alien atmospheres, industrial pollutants, or terraforming gases that would provide unmistakable evidence of technological civilization. These expanded search methods acknowledge a profound truth. We might have been looking for the wrong signals all along. A truly advanced civilization might not use radio waves for communication any more than we use smoke signals. They might have moved on to quantum entanglement, gravitational wave manipulation, or communication methods we haven't even imagined yet. But even as our search techniques become more sophisticated, we must confront the possibility that the very nature of advanced civilization might make it inherently difficult to detect. Perhaps intelligence, when it reaches a certain level of sophistication, naturally becomes less visible rather than more so. Consider our own trajectory. A century ago, our cities glowed with inefficient incandescent bulbs that scattered light in all directions. Today, we're moving toward LED lighting that can be precisely directed, reducing light pollution and making our urban areas dimmer when viewed from space. Our radio emissions, once broadcast indiscriminately in all directions, are increasingly replaced by fiber optic cables, satellite communications, and digital systems that leak much less energy into space. A truly advanced civilization might be almost invisible to our current detection methods. They might have learned to use energy so efficiently that they produce no waste heat detectable by infrared telescopes. They might communicate through methods that leave no electromagnetic signature. They might have developed technologies that work in harmony with natural processes rather than against them, making their presence nearly indistinguishable from the background cosmos. This possibility suggests that the Fermi Paradox might be less about the absence of alien civilizations and more about the limitations of our search methods. We might be like early radio enthusiasts listening for telegraph signals, unaware that the technology we're searching for became obsolete long before we learned to detect it. Recent years have brought another twist to the Fermi Paradox discussion: the increasing acknowledgement by government agencies that there are indeed objects in our skies that we cannot fully explain. The Pentagon's reports on unidentified aerial phenomena have documented hundreds of cases where military personnel have observed objects exhibiting flight characteristics that seem to exceed our current technological capabilities. These reports are careful to avoid claiming extraterrestrial origin for these phenomena. Most of the documented cases likely have conventional explanations: experimental aircraft, atmospheric phenomena, sensor malfunctions, or optical illusions. But a small percentage display characteristics that remain genuinely puzzling: objects that appear to move at impossible speeds, change direction without apparent propulsion, or operate in ways that seem to violate our understanding of physics. The scientific community has approached these reports with appropriate skepticism, but also with growing recognition that they deserve serious investigation. Harvard astronomer Avi Loeb has been particularly vocal about the need to study these phenomena scientifically rather than dismissing them out of hand. His argument is compellingly simple: if we don't understand what these objects are, we should invest in finding out, just as we invest billions in studying dark matter and other cosmic mysteries. This shift towards scientific openness about anomalous phenomena represents a significant change in how the search for extraterrestrial intelligence is conducted. Rather than focusing solely on distant signals from space, researchers are beginning to consider the possibility that evidence of alien technology might already be present in our immediate vicinity. The case of Oumuamua, the first confirmed interstellar object to pass through our solar system, provides another example of how strange discoveries can challenge our assumptions. Discovered in 2017, Oumuamua exhibited several unusual characteristics that defied easy explanation. Its shape appeared to be highly elongated, or perhaps flat like a pancake. It showed no signs of outgassing despite passing close to the Sun, yet it accelerated away from our star as if pushed by some invisible force. Most astronomers have settled on natural explanations for Oumuamua's behaviour, suggesting it might be a fragment of nitrogen ice from an alien Pluto-like world, or perhaps a particularly unusual type of comet. But its strange properties have sparked ongoing debate about how we might recognise truly artificial objects passing through our solar system. Avi Loeb has argued that Oumuamua's characteristics are consistent with what we might expect from an artificial light sail, a thin sheet of material designed to be pushed by starlight or stellar winds. While this interpretation remains controversial, it highlights an important point. As our detection capabilities improve, we're likely to encounter more objects and phenomena that don't fit neatly into our existing categories. The possibility that some of these anomalous objects might be artificial in origin brings us back to a fundamental question about the Fermi Paradox. What would alien technology actually look like to us? Our searches for extraterrestrial intelligence have largely been based on assumptions about how alien civilizations might behave and what technologies they might use. But these assumptions are necessarily limited by our own experience and imagination. We look for radio signals because that's how we communicate across long distances. We search for megastructures like Dyson spheres because that's how we imagine advanced civilizations might harness stellar energy. We monitor star systems for signs of industrial activity because that's the path our own civilization has followed. But what if alien intelligence has taken completely different evolutionary and technological paths? Perhaps the most profound limitation in our search for extraterrestrial intelligence is our assumption that alien minds would think in ways similar to our own. We expect them to be curious about the universe, to want to explore and communicate, to build monuments that demonstrate their technological prowess. But intelligence might not always lead in these directions. Consider the diversity of intelligence on our own planet. Octopuses are remarkably intelligent, capable of complex problem solving and tool use, but their intelligence is fundamentally different from ours. They're largely solitary creatures with no apparent interest in building permanent structures or accumulating knowledge across generations. Their intelligence is focused on immediate survival and adaptation rather than long-term planning or cosmic exploration. What if alien intelligence follows similar patterns? Perhaps the galaxy is filled with remarkably sophisticated civilizations that have no interest in space travel or interstellar communication. They might be content to explore inner space rather than outer space, developing rich virtual worlds and philosophical systems rather than rockets and radio telescopes. Or perhaps alien intelligence operates on timescales so different from our own that we're simply not patient enough to recognize it. If an alien civilization thinks and acts on geological timescales, their rapid response to our radio signals might not arrive for thousands of years. From their perspective, our entire technological civilization might appear and disappear in what seems like an instant. These possibilities remind us that the Fermi Paradox might be based on fundamentally anthropocentric assumptions about what intelligence looks like and how it behaves. We assume that intelligence naturally leads to technology, that technology leads to space exploration, and that spacefaring civilizations would want to communicate with other intelligences. But none of these assumptions are necessarily true. The search for extraterrestrial intelligence has always been as much about understanding ourselves as about finding others. Every assumption we make about how alien civilizations might behave reveals something about our own values, desires, and limitations. When we imagine aliens building vast megastructures, we're projecting our own drive to reshape our environment. When we expect them to broadcast their presence across the galaxy, we're assuming they share our loneliness and desire for connection. But perhaps the most important insight from decades of SETI research is how much we still don't know about the nature of life, intelligence, and civilization. The Fermi Paradox exists because we lack sufficient data to distinguish between competing explanations. We don't know how common life is in the universe. We don't know how often intelligence evolves. We don't know how long technological civilizations typically survive. Each new discovery in astronomy, biology, and planetary science provides another piece of this vast puzzle. The detection of organic molecules in interstellar space suggests that the building blocks of life are common throughout the galaxy. The discovery of extremophils on Earth, organisms that thrive in conditions once thought impossible for life, expands our understanding of where biology might emerge. The identification of potentially habitable exoplanets gives us specific targets for future searches. But perhaps the most significant developments are yet to come. The next generation of space telescopes will be capable of analysing the atmospheres of Earth-like exoplanets in unprecedented detail. If life is common in the universe, these instruments should be able to detect its signature in the form of atmospheric gases that can only be produced by biological processes. More intriguingly, these same telescopes might be able to detect technosignatures, atmospheric pollutants, or artificial compounds that would indicate the presence of industrial civilization on distant worlds. The detection of chlorofluorocarbons in an alien atmosphere, for example, would be difficult to explain through natural processes and might provide our first confirmed evidence of extraterrestrial technology. As our search techniques become more sophisticated and our understanding of life's possibilities expands, we might finally begin to answer the question that has haunted us since that lunch conversation at Los Alamos more than 70 years ago. But whatever answer we find, whether we discover a universe teeming with life or confirm our cosmic solitude, will fundamentally change our understanding of our place in the cosmos. The Fermi Paradox, in the end, might be less about finding aliens and more about finding ourselves. It forces us to confront deep questions about the nature of intelligence, the future of technological civilization, and the meaning of existence in a vast and largely empty universe. Whether we are alone or part of a vast cosmic community, the search itself reveals something profound about the human spirit. Our refusal to accept easy answers, our determination to push against the boundaries of the known, and our deep abiding hope that somewhere in the darkness, someone else is looking back at us, with the same wonder and curiosity that drives us to keep searching. And perhaps, as you lie there tonight contemplating these cosmic mysteries, that's enough. Perhaps the search itself, the questions we ask and the methods we develop to answer them, represents something precious and rare in the universe. Perhaps consciousness, that wonders about its place in the cosmos, is the most remarkable phenomenon of all, regardless of how often it occurs among the stars. As we drift deeper into this cosmic mystery, there's another possibility we haven't yet considered, one that's both more mundane and perhaps more unsettling than hidden alien civilizations or great filters. What if the answer to the Fermi Paradox isn't about the rarity of life or the dangers of technology, but about something far more fundamental, the nature of time itself and our fleeting moment within it? Consider this: the universe is approximately 13.8 billion years old, an almost incomprehensible span of time. Our entire species has existed for perhaps 300,000 years, and our technological civilization for barely a century. In cosmic terms, we've been listening for alien signals for less than the blink of an eye. We're like someone who walks into a vast library, glances at a single page of one book, and concludes that the entire collection must be empty of interesting stories. The temporal aspect of the Fermi Paradox becomes even more striking when we consider the lifespans of civilizations. Even if technological species are relatively common in the galaxy, they might exist in brief, widely separated bursts of activity. Imagine civilizations as fireflies blinking in a dark field. From any single firefly's perspective, the field appears empty and silent. But if you could watch the entire field across hours or days, you might see that it's actually full of light and activity, just spread out across time in ways that make simultaneous observation unlikely. This temporal mismatch could explain our cosmic loneliness without requiring us to believe that intelligence itself is extraordinarily rare. Perhaps the galaxy has been home to thousands of technological civilizations, but they've come and gone across billions of years, each one experiencing the same sense of isolation that we feel today. Their radio signals cross the empty space between stars long before our planet even formed, or they won't begin broadcasting until long after our sun has died. The mathematics of this possibility are sobering. If technological civilizations last on average a few thousand years, and if they're separated by millions of years in time, then the chances of two of them existing simultaneously within communication range become vanishingly small. We might be living in a universe that has been rich with intelligence throughout its history, but where that intelligence has been scattered across such vast spans of time that no two civilizations ever overlap. But perhaps even more intriguing is the possibility that we're asking the wrong questions entirely. Our search for extraterrestrial intelligence has been shaped by assumptions about what intelligence looks like and how it manifests itself. We expect aliens to build radio telescopes because we built radio telescopes. We expect them to be curious about the universe because we're curious about the universe. We expect them to want to communicate across interstellar distances because that's what we want to do. But what if intelligence, when it reaches sufficient sophistication, naturally turns inward rather than outward? What if the most interesting frontiers for advanced minds lie not in the vast expanses of physical space, but in the equally vast expanses of consciousness itself? Consider our own trajectory. As our understanding of the universe has deepened, we've discovered that the most profound mysteries lie not in distant galaxies, but in the nature of consciousness. The hard problem of subjective experience, the strange relationship between mind and matter. Perhaps alien civilizations, after mapping their local stellar neighborhood and cataloguing nearby worlds, conclude that the real adventure lies in exploring the infinite landscapes of thought itself. Such civilizations might develop technologies we can barely imagine, direct interfaces between minds, the ability to create rich simulated realities indistinguishable from physical experience, ways of expanding consciousness and perception that make interstellar travel seem crude and unnecessary by comparison. Why spend millennia crawling between the stars when you can create entire universes within the space of a single mind? This inward turn might be a natural phase in the development of intelligence. Young civilizations look outward, driven by curiosity and the desire to explore. But mature civilizations might look inward, having discovered that the most interesting questions aren't about what's out there, but about what's in here, in the mysterious depths of consciousness itself. If this is the case, then the galaxy might be full of extraordinarily advanced civilizations that have simply lost interest in the physical universe. They might exist in states of consciousness so elevated and complex that our radio telescopes and space probes are as irrelevant to them as ant trails are to us, not because they're hostile or secretive, but because they've moved on to more interesting pursuits. This possibility is both comforting and troubling. Comforting because it suggests that intelligence might indeed be common in the universe, that we're not alone in our cosmic curiosity. Troubling because it implies that our own future might lie not in the exploration of space, but in the abandonment of the physical world entirely. Yet there's another angle to consider, one that brings us back to the very nature of detection itself. Perhaps the reason we haven't found evidence of alien civilizations isn't that they don't exist, but that we're fundamentally misunderstanding what such evidence would look like. Our search strategies have been based on the assumption that advanced civilizations would be detectable through their technology or their deliberate attempts at communication. We look for radio signals, optical pulses, megastructures around stars, atmospheric pollutants on distant worlds. But what if truly advanced intelligence leaves a much subtler signature, one that we lack the sophistication to recognize? Think about how our own understanding of intelligence has evolved. A century ago, we might have defined intelligence purely in terms of tool use and problem solving. Today, we recognize forms of intelligence in systems we once considered purely mechanical. The way immune systems learn to recognize threats, the way ecosystems self-organize and adapt, the way markets process information and allocate resources. Perhaps alien intelligence operates on scales and through mechanisms that we don't yet recognize as intelligent at all. Maybe what we interpret as natural phenomena, the formation of galaxies, the behavior of stellar clusters, the patterns of cosmic rays, are actually the products of intelligence so advanced that it operates through the fundamental forces of physics themselves. This isn't to suggest that every natural phenomenon is artificial, but rather that our categories of natural versus artificial might be too crude to capture the full spectrum of how intelligence might manifest itself in the universe. An intelligence that has learned to work with gravity, electromagnetic fields, and quantum mechanics as easily as we work with fire and stone might create structures and processes that appear entirely natural to our current level of understanding. Such civilizations wouldn't need to build obvious megastructures or broadcast radio signals. They might encode information in the patterns of stellar formation, communicate through gravitational waves, or store data in the quantum states of matter across entire galactic regions. Their presence might be written into the very structure of space-time itself, invisible to us not because it's hidden, but because we lack the conceptual framework to recognize it as artificial. This possibility suggests that the solution to the Fermi Paradox might not lie in finding alien civilizations, but in developing new ways of thinking about intelligence, consciousness, and the relationship between mind and cosmos. We might need to expand our definition of life itself, moving beyond biology to encompass forms of organization and information processing that we haven't yet learned to recognize. Recent developments in our understanding of complex systems and emergence hint at these possibilities. We're beginning to recognize that intelligence might not be confined to biological brains, but could emerge from any sufficiently complex system capable of processing information and adapting to its environment. Artificial intelligence, quantum computers, even certain types of social networks might represent the early stages of new forms of intelligence that bear little resemblance to their biological origins. If this trajectory continues, our own civilization might eventually evolve beyond anything we would currently recognize as human intelligence. We might merge with our technologies, expand into digital realms, or discover ways of existing that transcend the boundaries between individual minds. From the perspective of such evolved beings, our current concerns about finding alien radio signals might seem as quaint as a child's desire to find fairies in the garden. But perhaps the most profound implication of the Fermi Paradox isn't about aliens at all, but about the nature of existence itself. The silence we observe might be telling us something fundamental about the structure of reality, the role of consciousness in the cosmos, and the ultimate destiny of intelligence. Some theories in physics suggest that consciousness might play a more fundamental role in the universe than we typically assume. Quantum mechanics, with its emphasis on observation and measurement, hints at deep connections between mind and matter that we're only beginning to explore. If consciousness is indeed a fundamental feature of reality rather than just an emergent property of complex brains, then the distribution of intelligence throughout the universe might follow patterns we haven't yet learned to recognize. Perhaps intelligence doesn't evolve from matter, but rather matter evolves from intelligence. Perhaps what we call the physical universe is actually the external manifestation of vast cosmic minds, and our search for alien civilizations is really a search for other aspects of our own deepest nature. Yes, these are speculative ideas, more philosophy than science, but they illustrate how the Fermi Paradox pushes us toward fundamental questions about the nature of reality itself. When we ask where all the aliens are, we're really asking what it means to exist, to be conscious, to be intelligent, in a universe that seems both perfectly suited for life and strangely empty of it. As our technology continues to advance and our search methods become more sophisticated, we may finally begin to answer these questions. The James Webb Space Telescope is already revolutionizing our understanding of exoplanet atmospheres and the potential for life beyond Earth. Future missions will probe even deeper, searching for biosignatures and technosignatures with unprecedented sensitivity. Artificial intelligence is transforming our ability to process the vast amounts of data generated by modern telescopes, finding patterns and anomalies that human observers might miss. Machine learning algorithms trained on millions of stellar observations can identify unusual objects and phenomena that might indicate artificial origin or biological activity. Even our understanding of life itself is expanding. The discovery of extramorphals, organisms that thrive in conditions once thought impossible for biology, has broadened our conception of where life might exist. We now know that life can flourish in the depths of the ocean, around volcanic vents, in highly acidic environments, in conditions of extreme radiation and temperature. This suggests that the habitable zone around stars might be much larger than we previously thought, and that life might emerge in environments we never considered searching. These advances bring us closer to answering the fundamental question posed by the Fermi Paradox, but they also reveal how much we still don't know. Each new discovery opens up new possibilities and new questions. The detection of phosphine in the atmosphere of Venus, initially thought to be a possible sign of life, turned out to have a more mundane explanation, but it demonstrated how quickly our understanding can shift when we encounter unexpected phenomena. The search for extraterrestrial intelligence has always been as much about understanding ourselves as about finding others. Every assumption we make about how alien civilizations might behave reveals something about our own nature, our values, our hopes and fears about the future. When we imagine aliens as explorers and communicators, we're expressing our own deepest desires to connect and understand. When we worry about hostile alien invasions, we're projecting our own history of conflict and conquest. But perhaps the most important lesson from decades of searching is that the universe is far stranger and more complex than we initially imagined. Every new discovery, from the first exoplanets to the recent detection of gravitational waves, has revealed phenomena that were barely conceivable just a few decades ago. The universe consistently surprises us, confounding our expectations and forcing us to expand our understanding of what's possible. This suggests that the answer to the Fermi Paradox, when it finally comes, might be equally surprising. We might discover that life is far more common than we thought, but takes forms we never expected. We might find that intelligence is everywhere around us, but operating through mechanisms we haven't learned to recognize. We might realize that we've been asking the wrong questions entirely, looking for the wrong signals in the wrong places at the wrong times. Or we might confirm our cosmic solitude, discovering that Earth is indeed a rare and precious anomaly in an otherwise lifeless universe. Such a discovery would be both humbling and terrifying, placing an enormous responsibility on our shoulders as possibly the only conscious witnesses to the beauty and complexity of the cosmos. Either answer would transform our understanding of our place in the universe and our responsibilities to future generations. If we are alone, then the preservation of human consciousness and culture becomes a cosmic imperative. If we are not alone, then learning to coexist with other forms of intelligence becomes one of our most important challenges. As you drift off to sleep tonight, perhaps you can find some comfort in knowing that these questions continue to drive scientific inquiry around the world. Radio telescopes scan the skies, space missions explore nearby worlds, and researchers work tirelessly to understand the conditions that give rise to life and intelligence. Whether we are alone or part of a vast cosmic community, the search itself represents something beautiful about the human spirit. Our refusal to accept ignorance, our determination to push against the boundaries of the known, and our deep, abiding hope that the universe holds wonders we haven't yet imagined. The Fermi Paradox remains unsolved, but perhaps that's as it should be. Some questions are more valuable for the search they inspire than for any final answer they might yield. In asking where all the aliens are, we're really asking who we are, why we're here, and what our future might hold among the stars. And those questions, regardless of their ultimate answers, remind us that consciousness capable of wonder might be the most remarkable phenomenon in the universe, whether it occurs once or countless times across the cosmic dark. The silence continues, vast and patient, waiting for us to develop the wisdom and technology needed to break it. Until then, we remain alone with our questions, our hopes, and our enduring faith that somewhere in the darkness, someone else might be looking up at the stars and wondering, just as we are, whether they are alone in the infinite night. The search for answers to the Fermi Paradox has taken us down many paths, each more intriguing than the last. But there's one avenue we haven't fully explored yet, one that might be the most unsettling of all. The possibility that we're not just alone in space, but alone in time as well. That we might be living in what cosmologists call a premature universe, where intelligence has emerged far earlier than it should have. This idea springs from a curious fact about cosmic history. The universe today is still relatively young in terms of its capacity to support life. Stars will continue forming for trillions of years into the future, far longer than the universe has even existed so far. Most of the stars that will ever burn haven't even been born yet. If life tends to emerge around longer-lived, more stable stars, then we might be among the very first intelligent beings to appear anywhere in the cosmos. It's a bit like arriving at a party just as the host is setting up the decorations. The main event hasn't even begun yet, and most of the guests won't arrive for hours. From our perspective, the party seems empty and quiet, but that's only because we're extraordinarily early. The real celebration lies far in the future, when red dwarf stars, which can burn for hundreds of billions of years, finally mature enough to support complex planetary systems. This temporal displacement could explain our cosmic loneliness without requiring any great filters or self-destructing civilizations. We might simply be the universe's early adopers, the first wave of consciousness to emerge in a cosmos that will eventually teem with intelligence. In this scenario, our apparent solitude isn't a sign of rarity or danger, but merely of timing. We're not alone because intelligence is impossible, but because we're impatient pioneers in a universe still preparing for its golden age of life. The implications of this possibility are both profound and oddly reassuring. If we truly are among the first, then the future of intelligence in the universe might largely depend on our choices and actions. We could be the elder civilization that future species will wonder about, the ancient ones who first asked these questions and began the long project of understanding the cosmos. But there's another temporal puzzle that adds complexity to this picture, the question of how we define civilization itself. When we search for alien intelligence, we're typically looking for signs of technology similar to our own. Radio telescopes, industrial pollution, megastructures around stars. But what if we're searching for the wrong stage of technological development entirely? Consider how rapidly our own technology is evolving. A century ago, we were just learning to harness electricity for communication. Today, we're developing quantum computers and artificial intelligence systems that operate in ways their creators don't fully understand. The pace of change is accelerating so rapidly that predictions about technology even 50 years in the future become almost meaningless. Now extrapolate this forward 1,000 years, or 10,000, or 1,000,000. What would a truly mature technological civilization look like? It might bear no resemblance whatsoever to our current understanding of technology. Instead of building massive structures or broadcasting radio signals, they might have learned to manipulate matter and energy at such fundamental levels that their activities would be indistinguishable from natural processes. They might have transcended the need for physical infrastructure entirely, existing as patterns of information that flow through the quantum foam of space-time itself. They might have learned to encode their consciousness into the cosmic microwave background radiation, turning the entire universe into a vast computational matrix. From our primitive perspective, such civilizations would be completely invisible, their presence woven so seamlessly into the fabric of reality that we couldn't detect them any more than a bacterium could detect our global internet. This possibility suggests that the Fermi Paradox might be less about the absence of alien civilizations and more about the limitations of our search methodology. We're looking for technological signatures that might represent only a brief transitional phase in the development of intelligence, a cosmic equivalent of searching for smoke signals in an age of fiber optic cables. But perhaps the most challenging aspect of the Fermi Paradox lies not in any specific explanation, but in what it reveals about the nature of scientific inquiry itself. The paradox exists because we're trying to use statistical reasoning to draw conclusions about a phenomenon for which we have exactly one data point: ourselves. It's like trying to understand the nature of rivers by studying only a single drop of water. Every calculation we make about the probability of alien life is necessarily based on assumptions drawn from our own experience. We assume that life requires liquid water because that's the only kind of life we know. We assume that intelligence leads to technology because that's what happened here. We assume that technological civilizations would want to communicate across interstellar distances because that's what we want to do. But each of these assumptions might be profoundly wrong. Life might emerge through chemical processes we've never imagined, in environments we consider completely hostile. Intelligence might develop along paths that have nothing to do with tool use or communication. Technological civilizations might naturally evolve in directions that make them completely undetectable to our current search methods. The humbling truth is that we don't know what we don't know. Our understanding of life, intelligence, and civilization is based on a sample size of 1, observed over a period of time that represents barely an instant in cosmic history. Drawing broad conclusions about the universe from such limited data is a bit like a mayfly trying to understand the nature of seasons based on its single day of existence. This recognition doesn't invalidate the search for extraterrestrial intelligence, but it does suggest that we should approach it with appropriate humility. The universe has consistently surprised us, revealing phenomena that were beyond our imagination just decades earlier. Black holes, dark energy, quantum entanglement, exoplanets, gravitational waves, all of these discoveries forced us to expand our understanding of what's possible. The answer to the Fermi Paradox, when it finally comes, will likely be equally surprising. It might involve forms of life and intelligence that exist outside our current conceptual framework. It might reveal that consciousness and intelligence are far more fundamental features of the universe than we currently suspect. Or it might confirm that we are indeed alone, at least for now, in our corner of a vast and largely empty cosmos. Recent developments in astrobiology have begun to hint at some of these possibilities. The discovery of complex organic molecules in interstellar space suggests that the building blocks of life are far more common than we once thought. The identification of subsurface oceans on moons like Europa and Enceladus has expanded our conception of habitable environments. The detection of seasonal methane variations on Mars has raised tantalizing questions about possible biological activity on our neighboring world. But perhaps the most intriguing developments have come from our growing understanding of extremophiles here on Earth. These organisms thrive in conditions that would be instantly lethal to most life forms. In boiling hot springs, in highly acidic environments, in the depths of the ocean where sunlight never penetrates, even in the radioactive cooling pools of nuclear reactors. Each new extremophile discovery expands the potential habitable zone around stars and suggests that life might emerge in environments we never thought to search. If organisms can thrive in the harsh radiation environment near a nuclear reactor, might they also flourish in the radiation-soaked environments around pulsars or in the outer atmospheres of gas giant planets? The possibilities multiply with each new discovery. These findings are beginning to influence how we search for life beyond Earth. The European Space Agency's upcoming missions to Jupiter's moons will drill through kilometers of ice to sample the hidden oceans beneath. NASA's Perseverance rover continues to collect samples from Mars that will eventually be returned to Earth for detailed analysis. The James Webb Space Telescope is beginning to analyze the atmospheres of potentially habitable exoplanets, searching for chemical signatures that might indicate biological processes. But even as our search techniques become more sophisticated, we must confront a fundamental limitation: the vast scales of space and time involved. Even if the galaxy is filled with life, the distances between stars are so enormous that detecting it requires extraordinary sensitivity and patience, Light from the nearest star system takes over 4 years to reach us. Radio signals, travelling at the same speed, face the same delay. This means that any communication with alien civilizations would unfold over timescales that dwarf human attention spans. A simple conversation would require decades or centuries to complete. The exchange of complex information, the kind needed to establish genuine understanding between different forms of intelligence, might take millennia. This temporal barrier adds another layer to the Fermi Paradox. Even if alien civilizations exist and are actively trying to communicate, the vast delays involved might make meaningful contact impossible. By the time we received a message from a distant civilization, they might have evolved beyond recognition or ceased to exist entirely. By the time our reply reached them, we might face the same fate. These considerations have led some researchers to focus on searching for signs of past rather than present civilizations. If intelligence tends to be short-lived on cosmic timescales, then we might be more likely to find the archaeological remains of alien societies than their living representatives. This has sparked interest in searching for what scientists call technosignatures, the long-lasting traces that technological civilizations might leave behind. These could include changes to planetary atmospheres that persist long after their creators are gone, artificial structures that remain visible for millions of years, or even deliberate messages encoded into stable physical systems designed to survive the collapse of their parent civilizations. Such archaeological approaches to SETI represent a fundamental shift in thinking, from searching for living aliens to searching for evidence that they once existed. The concept of cosmic archaeology also raises intriguing questions about our own legacy. What traces will human civilization leave behind for future archaeologists to discover? Our radio emissions will fade into the cosmic background within a few light years of Earth. Our cities will crumble to dust within a few thousand years. Even our most durable achievements, like the faces carved on Mount Rushmore or the Great Wall of China, will be erased by geological processes within a few million years. If we want to leave a message for future cosmic archaeologists, we need to think in terms of geological rather than human timescales. Some researchers have suggested encoding information in synthetic isotopes with extremely long half-lives, or in the orbital patterns of asteroids, or even in the genetic code of extremophile organisms that might survive long after more complex life has vanished. But perhaps the most enduring legacy we could leave would be life itself. If we succeed in spreading Earth-originated life to other worlds, either through deliberate terraforming projects or through the inevitable contamination that will accompany human space exploration, we might seed the galaxy with biological signatures that persist for billions of years. Future alien archaeologists might recognize these signatures as evidence of an ancient technological civilization, even if all other traces of our existence have vanished. This possibility adds a new dimension to discussions about planetary protection and the ethics of space exploration. Every mission we send to other worlds carries with it the potential to contaminate pristine environments with Earth-based microorganisms. While we currently treat this as a problem to be avoided, it might actually represent our best chance of leaving a lasting mark on the cosmos. The question then becomes, what kind of mark do we want to leave? If we are indeed alone in the galaxy, then our choices about how to explore and potentially colonize other worlds will determine the future character of intelligence in our cosmic neighborhood. We might be the seeds from which all future galactic civilization grows. This responsibility is both thrilling and terrifying. If we make wise choices, we could be the ancestors of a galactic community that endures for billions of years, spreading life and consciousness throughout the Milky Way and beyond. If we make poor choices, if we destroy ourselves or damage the environments we encounter, we might foreclose the possibility of intelligence ever flourishing in our region of space. The Fermi Paradox, in this light, becomes not just a question about where all the aliens are, but a mirror reflecting our own potential futures. Every possible explanation for the cosmic silence tells us something about the challenges and opportunities that might lie ahead for our own species. If the great filter lies behind us, then we might be among the few species lucky enough to have survived the transition from simple to complex life, from chemistry to biology, from biology to intelligence. Our future might be limited only by our own wisdom and determination. If the great filter lies ahead of us, then we face challenges that have destroyed countless other promising civilizations. Our survival might depend on our ability to navigate dangers that we're only beginning to recognize: climate change, nuclear warfare, artificial intelligence, biotechnology, or threats we haven't even imagined yet. If we are being observed by hidden alien civilizations, then our actions might be under constant scrutiny, evaluated by intelligences far older and wiser than ourselves. Our readiness for contact might depend on our ability to mature as a species, to overcome our tribal instincts and planetary thinking. If the universe is a dark forest filled with hostile civilizations, then our radio broadcasts over the past century might have already sealed our fate. Our survival might depend on learning to hide, to develop technologies that don't announce our presence to potential predators. Each of these possibilities suggests different strategies for our future development as a species. Some encourage bold exploration and loud declarations of our presence. Others counsel caution, stealth, and careful preparation for challenges we can barely imagine. But perhaps the most important insight from the Fermi Paradox is that we are participants in this cosmic story, not just observers. Our choices matter, not just for our own survival, but potentially for the future of intelligence in the universe. We might be writing the opening chapters of a story that will unfold across billions of years and countless worlds. This realization transforms the Fermi Paradox from an abstract scientific puzzle into a deeply personal question about our responsibilities and aspirations. When we ask where all the aliens are, we're really asking what kind of future we want to create, what kind of legacy we want to leave, what kind of cosmic citizens we want to become. The answer, whatever it turns out to be, will depend as much on our values and choices as on the fundamental laws of physics. We are not just searching for alien intelligence, we are in the process of becoming it ourselves. The universe is watching, waiting to see what we'll do next. And in that watching, in that waiting, in the vast patient silence between the stars, perhaps we can find both humility and hope. Humility because we are so small and young in cosmic terms. Hope because we might be the beginning of something extraordinary. The first notes in a symphony of consciousness that will eventually fill the galaxy with music. Tonight, as you drift towards sleep, you might find some peace in knowing that this ancient question continues to drive human curiosity and scientific discovery. Radio telescopes sweep the skies, space missions explore distant worlds, and researchers work tirelessly to understand the conditions that give rise to life and intelligence. Whether we are alone or part of a vast community of minds scattered across space and time, the search itself represents something beautiful about consciousness. Our refusal to accept ignorance, our determination to reach beyond the boundaries of the known, and our deep, persistent hope that the universe holds wonders we have yet to discover. The great silence continues, vast and patient, filled with possibilities we can barely imagine, until we break that silence, either by finding others or by spreading our own voices among the stars. We remain alone with our questions, our dreams, and our enduring faith that somewhere in the darkness the universe is preparing to surprise us once again. As our cosmic journey draws toward a gentle close, there's one more possibility worth considering as you settle into the quiet comfort of your evening thoughts. Perhaps the most beautiful resolution to the Fermi Paradox isn't found in any single explanation, but in the recognition that the question itself represents something extraordinary about the nature of consciousness. Think about it for a moment. In all the vastness of space across billions of years of cosmic history, matter has organized itself into patterns complex enough to contemplate their own existence. Atoms forged in the hearts of dying stars have arranged themselves into brains capable of wondering about other brains on distant worlds. The universe has quite literally awakened to itself through us, developing the capacity to ask whether it has done so elsewhere. This emergence of self-aware matter might be so improbable, so delicately balanced on the edge of possibility, that it occurs only rarely across the cosmic landscape, not because of any single great filter or catastrophic failure, but because consciousness itself might be a phenomenon that teeters on the very boundaries of what the laws of physics allow. Consider the chain of events that had to unfold for you to be lying there tonight, pondering the silence between the stars. The universe had to expand at just the right rate after the Big Bang, neither collapsing back on itself nor flying apart so quickly that stars could never form. Nuclear forces had to be precisely calibrated to allow the formation of elements heavier than hydrogen. Gravity had to be strong enough to pull matter together into stars and planets, but weak enough to allow complex structures to persist. On Earth specifically, countless additional coincidences had to align. Our planet needed to form at just the right distance from a star of just the right type. We needed the stabilizing influence of our unusually large moon, the protective embrace of Jupiter's gravitational field, the slow churning of plate tectonics to regulate our climate. We needed ice ages to drive evolution, asteroid impacts to clear ecological niches, and volcanic activity to cycle nutrients through our biosphere. But even with all these favourable conditions, the path from simple chemistry to complex consciousness was neither straight nor inevitable. Life on Earth remained stubbornly simple for billions of years. The transition from prokaryotic to eukaryotic cells happened perhaps only once in our planet's history. The evolution of multicellular life, sexual reproduction, nervous systems, and finally self-aware intelligence each represented leaps that might have been vanishingly unlikely to occur. When viewed from this perspective, the Fermi Paradox becomes less puzzling and more poignant. We might indeed be alone, not because the universe is hostile to life, but because consciousness represents such an improbable flowering of complexity that it occurs only in the rarest of circumstances. We might be the universe's way of knowing itself, a singular achievement in a cosmos that has tried countless times, but succeeded only here, only now, only us. This possibility carries with it a profound sense of responsibility. If consciousness truly is rare in the universe, then every act of awareness, every moment of wonder, every question asked about our place in the cosmos becomes precious beyond measure. We are not just observers of the universe, but its only witnesses, the sole means by which 13.8 billion years of cosmic evolution comes to know and understand itself. But there's another way to think about our apparent solitude that's equally moving and perhaps more hopeful. Maybe the reason we haven't found other civilizations isn't that they don't exist, but that the universe is still in its infancy when it comes to supporting complex life. The cosmos may be preparing for a future golden age of consciousness that we can barely imagine. Most of the stars that will ever shine haven't been born yet. The red dwarfs that will burn for hundreds of billions of years are just now reaching the stability needed to support complex planetary systems. If intelligence tends to emerge around longer-lived, more stable stars, then we might be among the very first conscious beings to appear anywhere in the universe. We're not late to the cosmic party, we're incredibly early, arriving just as the decorations are being hung and the music is being tuned. In this scenario, our loneliness is temporary, a brief interlude before the universe fills with voices we cannot yet imagine. We might be the ancient ones that future civilizations will wonder about, the mysterious first consciousness that began asking the deep questions and started the long conversation between mind and cosmos. Whether we are alone or simply early, whether consciousness is extraordinarily rare or just remarkably young, the implications are similar. We find ourselves in the profound position of being among the first minds capable of contemplating the universe's history and imagining its future. We are the cosmic dawn, breaking after a long night of unconscious matter and energy. This realization transforms how we might think about our responsibilities to future generations and to the cosmos itself. Every choice we make about how to develop our technology, how to treat our environment, how to spread beyond our home world, becomes a decision about the future character of intelligence in the universe. We are not just living our own lives, but potentially shaping the template for all conscious life that might follow. The search for extraterrestrial intelligence, from this perspective, becomes more than just a scientific endeavour. It becomes an act of cosmic gardening, a way of preparing the ground for the conversations that might one day bloom across interstellar space. Every radio telescope we build, every exoplanet we discover, every step we take toward understanding the conditions that give rise to life helps create the foundation for a future community of minds. Perhaps the most beautiful aspect of this cosmic gardening is that it doesn't require us to find alien civilizations to be meaningful. The search itself, the questions we ask and the methods we develop to answer them, represent something precious and rare in the universe. Consciousness turning its attention outward, matter becoming curious about matter, the cosmos developing the capacity to marvel at its own existence. As you drift towards sleep tonight, you might find comfort in knowing that you are part of this extraordinary phenomenon. Your thoughts, your questions, your capacity for wonder represent one of the most remarkable achievements in the history of the universe. In pondering the Fermi Paradox, in wondering about our place among the stars, you are participating in the cosmos coming to know itself. The great silence between the stars continues, patient and vast, filled with possibilities we can barely imagine. But within that silence, on this small blue world orbiting an ordinary star in an unremarkable galaxy, something extraordinary has awakened. Consciousness has emerged from the cosmic dark, bringing with it the capacity to ask questions, to seek understanding, to reach across the void with radio waves and mathematics and hope. Whether we are alone or part of a vast community of minds scattered across space and time, this awakening represents something beautiful beyond measure. We are the universe becoming aware of itself, matter organizing into patterns complex enough to contemplate their own existence. We are stardust that has learned to wonder about stars. In that wondering, in that reaching toward the unknown, we find both our cosmic significance and our deepest humanity. The Fermi Paradox may never be fully resolved, but in asking the question, in refusing to accept easy answers, in maintaining our faith that the universe holds wonders we have yet to discover, we demonstrate something remarkable about the nature of consciousness itself. And perhaps that's enough. Perhaps the search is more valuable than any answer we might find. Perhaps consciousness capable of wonder, capable of reaching beyond the boundaries of the known, capable of asking why the night sky is so beautifully, mysteriously quiet, is the most extraordinary phenomenon in the universe, whether it occurs once or countless times across the cosmic dark. The stars continue their ancient dance above us, burning bright in the infinite night. The radio telescopes continue their patient listening, scanning frequencies for whispers from distant worlds. The space missions continue their slow journey outward, carrying our curiosity to moons and planets that have waited billions of years for visitors. And somewhere between the questions and the searching, between the longing and the wondering, between the vast silence of space and the small bright spark of consciousness that contemplates it, we find our place in the cosmic story. Not as the centre of the universe, but as its awakening mind. not as the only intelligence that matters, but as intelligence that has learned to matter. Not as the answer to the cosmic mystery, but as the part of the mystery that has learned to ask questions. Sleep well, fellow traveller, in this strange and beautiful cosmos. Tomorrow, the search continues, the questions persist, and the universe waits patiently for consciousness to grow a little wiser, reach a little further, wonder a little more deeply about the nature of existence itself. In that wondering, we are never truly alone, for we carry within us the curiosity of the cosmos and the hope that somewhere in the darkness, someone else might be looking up at the stars and asking, just as we do, whether they are the only ones awake in the infinite night. The silence we've explored tonight is profound, but it's not empty. It's filled with the echoes of our own curiosity, the whispers of possibilities we're only beginning to understand, and the quiet hum of a universe that might be far stranger and more wonderful than we dare imagine. As we draw our gentle journey through cosmic mysteries to a close, let me ask you once more, where in the world are you listening from tonight? Whether you're tucked beneath blankets in Berlin as midnight approaches, or perhaps it's early morning in Seoul, and you're greeting the day with cosmic contemplation, you're part of something beautiful. All of us, scattered across this pale blue dot, united in our wonder about what else might be out there in the dark. The Fermi Paradox, this elegant puzzle that has guided our evening's exploration, reminds us that the most profound questions don't always have tidy answers. Sometimes, the beauty lies not in solving the mystery, but in living within it, in maintaining our sense of wonder, even when faced with cosmic silence. Perhaps that's the most human thing of all, our refusal to accept the darkness as final, our persistent hope that somewhere beyond the next star, around the next discovery, answers await. Tonight we've wandered through possibilities both comforting and unsettling. We've considered that we might be alone in a universe vast beyond comprehension, the only witnesses to 13.8 billion years of cosmic evolution. We've pondered whether we're simply early arrivals to a party that hasn't truly begun yet, pioneers in a cosmos still preparing for its golden age of consciousness. We've explored the darker corners of possibility, where silence might be a survival strategy and the universe a more dangerous place than our optimistic hearts would like to believe. But in all these wanderings, one thing remains constant: the extraordinary nature of consciousness itself. The very fact that matter can organize itself into patterns complex enough to ask these questions, to reach across interstellar distances with radio waves and hope, to lie awake at night wondering about its place in the cosmic story. This might be the most remarkable phenomenon in the universe, whether it happens once or countless times across the stellar void. We are part of something ancient and ongoing, this slow awakening of the cosmos to itself through the emergence of minds capable of wonder. Every time we look up at the stars and ask why they're so quiet, every time we build a telescope or launch a space mission, or simply pause to contemplate our place in the vastness, we are participating in the universe's attempt to understand itself. The search for extraterrestrial intelligence continues in laboratories and observatories around the world. Radio telescopes sweep the skies with patient persistence. Space missions carry our curiosity to distant worlds. Researchers work tirelessly to decode the conditions that give rise to life and consciousness. Whether they find evidence of other minds among the stars or confirm our cosmic solitude, the search itself represents something beautiful about the nature of awareness, our refusal to accept ignorance, our determination to reach beyond the boundaries of the known. So as your thoughts begin to soften and drift towards sleep, know that you've been part of this ancient conversation tonight. In wondering about aliens and cosmic silence, in contemplating the mysteries of consciousness and the nature of existence itself, you've joined a tradition that stretches back to the first human who looked up at the night sky and wondered what those distant lights might be. The great silence continues, vast and patient, and full of possibilities we can barely imagine. But within that silence, on this small world spinning through space, something extraordinary persists. Minds capable of wonder, hearts that refuse to accept easy answers, consciousness that insists on asking the biggest questions of all. Whether we are alone or part of a cosmic community we have yet to meet, whether the universe is young or old, dangerous or welcoming, one thing remains beautifully certain. Somewhere in the vast darkness between the stars, on a planet circling an ordinary sun, intelligence has awakened and learned to ask questions about its own existence. That awakening, that questioning, that persistent hope for connection across the cosmic void might be the most precious thing in the universe, and that might be reason enough to sleep peacefully tonight, knowing that in asking these questions, in maintaining our wonder despite the silence, we are fulfilling perhaps the most important role consciousness can play in the cosmos. We are the universe's way of marveling at itself, of reaching toward understanding, of refusing to let the darkness have the final word. So rest well, dear fellow wanderer among the stars. Tomorrow brings new discoveries, new questions, and perhaps even new whispers from the cosmic dark. The telescopes will continue their patient vigil, the spacecraft will carry our curiosity ever outward, and somewhere in a laboratory or observatory, a researcher might just detect the faintest signal that changes everything we thought we knew about our place in the universe. Until then, we have this moment, this quiet contemplation beneath ancient starlight, this shared wondering about what it means to be conscious in a cosmos so vast and mysterious. We have the privilege of being the part of the universe that has learned to ask questions, and perhaps in the end, that questioning itself is the answer we've been searching for all along. If you found some peace in this gentle exploration of cosmic mysteries, I'd be quietly grateful if you shared it with others who might need a moment of wonder in their evening routine. Subscribe if you'd like more of these sleepy journeys through the universe's biggest questions, and let me know in the comments what cosmic mystery you'd like us to explore together next. The stars are still there, patient and bright, waiting for us to grow wise enough to understand their secrets. And somewhere in that waiting, in that growing, in that endless reaching toward knowledge and connection, we find our purpose in the cosmic story. Sleep well and dream of distant worlds where other minds might one day look up at their own night sky and wonder, just as we do, whether they are truly alone in the infinite, beautiful, mysteriously quiet universe we all call home.